Black holes, those mysterious cosmic pockets of space where gravity is so strong, not even light can escape. They're a staple of science fiction, but in reality, they're a lot more fascinating than we often give them credit for. And today, I want to tackle one of the most mind-blowing aspects of black holes, the idea that they can evaporate into thin air. Do black holes really evaporate? And if so, how does this process work according to current scientific understanding? It's a question that has sparked a lot of debate and curiosity in the scientific community, and today, we're going to dive into the heart of this phenomenon. But before we do, it's essential to understand the context. Black holes are formed when a massive star collapses in on itself, creating a singularity, a point of infinite density and zero volume. The gravity of this singularity is so strong that it warps the fabric of space-time around it, creating an event horizon, a point of no return. But what happens once something crosses the event horizon? Well, that's where things get interesting. The laws of physics as we know them start to break down, and the rules of quantum mechanics take over. It's a realm where the strange and the unknown reign supreme. And it's precisely here where the concept of black hole evaporation comes into play. The idea is that black holes aren't eternal objects, but rather, they have a lifespan, a finite time before they disappear into nothingness. One of the key theories surrounding black hole evaporation is Hawking radiation. This theory, proposed by the legendary physicist Stephen Hawking, suggests that black holes emit radiation due to quantum effects near the event horizon. This radiation slowly drains the black hole's energy, causing it to shrink over time. But how does this process work, exactly? Well, it's all about the nature of space-time and the way it's affected by gravity. According to Hawking's theory, the event horizon of a black hole is not a fixed boundary but rather a fuzzy region where space-time is constantly fluctuating. These fluctuations give rise to virtual particles that are created from the energy of the black hole itself. Normally, these particles would annihilate each other, but near the event horizon, one of the particles gets trapped inside, while the other escapes as radiation. Over time, this process slowly drains the black hole's energy, causing it to evaporate. The implications of black hole evaporation are profound and far-reaching. If black holes can indeed evaporate, it challenges our understanding of the universe on a fundamental level. It means that information that falls into a black hole is not lost forever, but is instead preserved in the radiation that's emitted. This idea has sparked a lot of debate in the scientific community, with some arguing that it resolves the infamous black hole information paradox. But what does this mean for our understanding of the universe? For one, it suggests that black holes are not eternal objects but rather temporary ones that have a beginning, a middle, and an end. It also implies that the information contained within a black hole is not lost, but is instead preserved in the radiation that's emitted during evaporation. This idea has far-reaching implications for our understanding of the cosmos and the nature of space-time itself. In conclusion, the concept of black hole evaporation is a fascinating and complex phenomenon that continues to intrigue scientists and theorists alike. While we've made significant progress in understanding this process, there's still much to be learned, and it's an area of research that will likely continue to evolve in the years to come. Thanks for joining me on this journey into the heart of black holes. If you have any thoughts or questions about this topic, please leave them in the comments below. And if you want to explore more mind-bending concepts like this, be sure to check out my other videos on topics like dark matter and dark energy.